Continuing our conversation about VESPR theory, I now want to talk about the lone pairs in molecules and how that impacts the bond angles and also the geometry names that we use. So lone pairs are going to just take up more space around the central atom than a bonding pair of electrons. That's because those bonding electrons are attracted to two nuclei. And so that kind of changes the shape that it might kind of take up in space. Whereas something with a lone pair, we can envision taking up even more space like this. This doesn't really match with our picture of orbitals shapes very well, to be fair. But it will match kind of our idea of hybridized orbitals later on when we introduce those next chapter. So it's important to know that those lone pairs are going to take up more space. And because of that, they affect the overall geometry of the molecule and the bond angles. And these lone pairs are just electron groups like these bonding electrons as well. And so they they affect the shape of the molecule. But we can't see them spectroscopically or crystallographically as chemists. So, like when we try to visualize and study a molecule, we can easily see the nuclei if we take a crystal of the compound and we shoot X rays at it. But we don't see those lone pairs. And so our naming conventions are based on atoms bonded to a central atom and not the lone pairs. And so we have a set of names to describe geometries that, while it's the same number of electron groups, if some of them are lone pairs, we'll have a different geometry name because we're describing the shape that we're seeing for just the atoms that are bonded to the central atom itself, which can be a little bit confusing. And that's where this language of the electron group comes in to be like, here's how we see how the shape forms, but our name for the shape is going to be based on the atoms. So in terms of how electron group repulsions vary, we can say that our lone pair repulsions are the largest. Then lone pair, bonding pair are the second largest, and bonding pair have the least repulsions because of the amount of space those electrons can occupy in space. Seems really repetitive. So an example of this was the water molecule we're looking at that had 4 electron groups bonding to it. But so this oxygen here has 4 groups. 2 of them are lone pairs. So the only thing you would see if you were to study this molecule would be the nuclei of the hydrogen, oxygen, and hydrogen. And so the shape you would see here would be bent. And so we call these 4 electron group structures where only 2 of them are atoms, and they're in this arrangement, they're about 104 to 109 degrees in terms of a bond angle. We give it a bent geometry name rather than tetrahedral. So tetrahedral will only apply when all of the 4 electron groups are atoms. If only 2 of them are atoms, it'll be bent. So let's walk through now the many geometry names that we have once we start incorporating lone pairs. And what we're going to track in this conversation is the number of bonding domains, and this is really the electron groups. And we're going to be tracking the number of non-bonding domains, which together make up the total number of electron groups. So the bonding domains are the things that are going to be bonded atoms. And the non-bonding, I switched those. The bonding domains will be bonded atoms. And the non-bonding domains will be our lone pairs. So looking at these right here, both of these have electron groups of 3. So we have 3 electron groups for both of these. And this is what we'll do. We'll just break this down based on the number of electron groups and then show you the different types of geometries that we have with them and highlight their names. So let's take a look at one we already discussed, which is the trigonal planar. I'm going to change this. I have 3 atoms bonded to a central atom. They're 120 degrees apart. So what happens when one of those is replaced with a lone pair like this? So this is representing my lone pair, taking up more space. And then I have 2 bonded atoms, but I still have 3 total electron groups. So they're still going to arrange themselves about 120 degrees apart. But when I'm studying this, I'm not going to call it trigonal planar. I'm going to call it bent. Or since we have another bent, remember from the water, bent or V-shaped. And depending on the book, you'll see a preference. Both names work fantastically for me. And you'll see a bond angle a little bit less than 120 because that lone pair takes up more space, which pushes these atoms a little bit closer together than the 120 bond angle. Okay, so now we are looking at electron groups that have, 4 electron group category. So remember, the one we discussed already was tetrahedral. It has 4 atoms bonded to it, and it has about 109.5 degree bond angle to it. So now let's go through and start replacing these with lone pairs. So if I add 1 lone pair instead of a bonded atom, I get something that looks like this. It still looks like a little triangle pyramid, but a much, much, much shorter one. And so the name that we give this one is trigonal pyramidal. And the bond angles will be close to 109.5, but a little bit less just because of the space that this one is taking up. And honestly, you don't actually know what those bond angles are until you study it. Like the atoms that are bonded to it, the size of the central atom, all influence that bond angle. So I don't believe we can say there's a very rigid bond angle for all trigonal pyramidal structures. They vary. All right, so what if we replace that with 2? Then we would have water. Okay, so if we have 2 lone pairs, see there they are, they look like little wings. There we go, or Mickey Mouse ears. We're going to get that bent shape we described with water, right? Right here. And so anything that has 4 electron groups, but 2 of them are lone pairs, is going to be called bent. And again, it's going to have a bond angle less than 109.5. All right, let's move on to things that have 5 electron groups instead. So here we go. So the structure that we looked at before was this trigonal bipyramidal one, right? So it has 5 things bonded to a central atom, and we call it trigonal bipyramidal. And it has bond angles of 90 and 120 degrees. So there are a couple ways we can replace this with lone pairs. Let's take one out of what we call the equatorial plane, right here. So now we have a structure that honestly, I always think of it as a little seesaw in a way. So I'm holding it by its lone pair. So this one is going to be called a distorted tetrahedron. You can imagine that if one of these moved up a little bit more, we could start to create that tetrahedral structure. And we have 4 atoms bonded, right? So it's going to be similar to a tetrahedral, but it doesn't have the same bond angles. So there are bond angles that are less than 90 degrees, essentially, in some of these right here. And then this one will be a little bit less than 120 degrees. The other name for this that I like a little bit more is seesaw, because it's shorter and it's fun. So some other things that we can do with this is we can keep replacing these equatorial ones with lone pairs. So now I have 2 lone pairs on this one. You can see them right there. And I have 3 atoms that are bonded. I still have 5 electron groups, but look at this. I really only have those 4 to name it off of. And so this one, it forms a perfect T. So we just call it T-shape. And our bond angles here are about 90 degrees in this case. So we can keep removing these and adding more lone pairs, although I believe I have not. Perfect. All right, so now I've got 3 lone pairs on this one, and now we have a familiar shape. We only have 2 atoms bonded to each other. We have 5 electron groups, but they have now created something that appears to be linear with a bond angle of 180 degrees. So when something's linear, it doesn't necessarily mean it has 0 lone pairs. It could have 3 lone pairs instead. All right, let's switch gears to our 6 electron groups. So remember, this was our octahedral structure right here when it had all 6 as bonded atoms, and it looks basically like a diamond or a pyramid that's both upside down and right side up, or an 8-sided die if you play certain games. So our octahedron is our simple version. Now, what happens when we start removing these and adding lone pairs? Well, the first one that we create is called square pyramid. And so it has 5 electron groups. One of these is a lone pair, and it literally is a square with a top. And so it makes a perfect pyramid. We call it square pyramid. And our bond angles here are still about 90 degrees. Now, if we were to remove a second one and replace it with a lone pair, the shape we would be looking at would look like a square. So these lone pairs aren't going to be visible, right? You're just going to see these atoms all bonded in the same plane. And so they're going to be 90 degrees apart. We call this square planar. So our bond angle becomes 90 degrees still, which is the same as our octahedral one. So our bond angles aren't really shifting as we're changing the number of lone pairs because we have so many things. It's such a crowded central atom that everything's still about 90 degrees.